Alright, so this is chapter 12, video lecture. This is going to cover our chemical kinetics. You will notice that there's actually two more chapters in this General Chemistry 2 that are going to be building off of these chemical kinetics. However, let me preface that by saying that while the chemical kinetics chapter is conceptually probably one of the most important chapters you will learn this semester, and will allow you to really increase your understanding of the world and universe around you to a degree that really no other chapter quite accomplishes. If you truly understand this chapter, a lot of the mystery of the world and universe around you opens up to you a little bit. This is probably one of the most single conceptually important chapters, period. However, the math, the it's very math heavy. This is typically a chapter people have a lot of problems with, which is okay. That's one of the reasons I have it separated out so you can limit the damage, as it were. That's why I do that 6 exams, drop 2 usually, or I have some sort of drop exam mechanism. Is because this chapter does tend to be one where some people just, no matter how you explain, um, go, this is hard, and then turn off and just cannot go further. And if they come back sometimes later on after, letting it cool in the back of their head for a year or two, typically then people get this chapter much better. But unfortunately, in a limited time period of a semester or even a summer semester, which is even worse, uh, this is the chapter that people typically just find extremely challenging because it is such a departure from everything that you have ever learned before. So, again, table of contents. Now, this chapter, when we talk about reaction rates, we are going to want to be able to quantify these. And so, this is going to be measured in the change in concentration of reactant or product per unit of time. Hopefully, okay, this is the perfect example of this chapter, really. This rate right here, reaction rate. How do you measure the rate of anything? How do you measure how fast your potato chips are disappearing, or how fast you're speeding along the highway, or any rate at all? Well, you always measure the change in the distance, the amount that's disappearing, etc., over a change in time, right? And so, really be truthful to yourself. How many of you that are listening to this, when I said the rate is measured in the change in concentration of a reactant or a product per unit of time, thought, oh my God, that is unbelievably difficult. I started blanking out. I bet a lot of you, if you're really being honest. And the funny part about this is this is something that you're actually incredibly familiar with if you've ever driven, or really even if you're just eating popcorn, you're sort of gauging and measuring that. If you're eating food, you're gauging that and going, well, I gotta go to the grocery store next week because my food's disappearing about that fast. This is not something that should have been difficult, right? This is actually extremely easy, but because it's now in scientific terminology, it seems much, much harder, doesn't it? All right, so again, let's say you have a reactant A and that's colorful. You're going to measure it and how fast A disappears. That's how fast the reaction is going. How are you going to measure something if you have a product that's very colorful and you can see or detect? Well, you're going to measure it on how fast that product's being made, right? And so you literally look, okay, the 50% increase in product over a 10-minute period. Cool. That would be a reaction rate. Now, again, these are just what the symbols here mean. Remember, delta means change in. This right here means a concentration. That's what brackets always mean, actually. So whenever you see these brackets and then some species, in this case we're talking about A, but this could be an O2 as an oxygen gas. This also could be like H2O, okay? Doesn't matter, it's a reactant or product. And again, this is over time, change in time. Whenever you see a change in time, changes are always final minus initial. Or another way of saying that is the second state minus the first state. That's all that is. It's actually not anything that has to be magical or difficult. So right here we see an example of a reaction. We have times, literally what we've done is every 50 seconds we measured concentrations. There you go. That's the sort of thing you do in a lab, okay? And so this is the reaction that's taking place, and this is what we're seeing in this table. So the reaction is we have NO2s, two of them. When they react, they're going to make NO, two NOs, and a single O2. This happens at 300 degrees Celsius. Typically, in most problems that you're going to do, the temperature itself won't be a factor. Why the temperature's there is because it would make a big difference, won't it? So you all probably know that if you put the burner on high, you burn it, the chicken, right? Or the veggie meal or whatever you want to make, okay? Doesn't matter, stir fry, anything. If you put the burner on medium, you cook it exponentially slower, don't you? So high, you burn it after a couple minutes. Medium takes 10-20 minutes to burn, doesn't it? So it's a big difference from a relatively small temperature difference because reaction rates change exponentially with temperatures. And we'll talk about that in just a bit. But the important part here is to understand how to read tables. Now, this is actually one of the main skills that science majors are somewhat known for, and this is one of the reasons that we tend to get hired on just pretty much everywhere. If you have a science major, you can usually find a job. I have never actually graduated a single science major that could not find a job within a couple months, and that paid relatively well and could go up and become, a boss and up, further and up. The only time I ever had anybody that took more than a single month actually was they refused to move out of a small town in the middle of nowhere, Tennessee. It's the first time I ever saw somebody struggle to find a job as a science major. Normally my science majors, especially the chemistry majors I graduate and keep track of, they find jobs within a week or two. And part of that is our ability to understand tables and graphs, which are very useful tools to transmit knowledge quickly and easily. So right here we're looking at time. When we look at this time plus minus 1 second, that means that this 0 is plus or minus 1 second. This 1 second's probably because it takes about a second for a person to register and actually stop a timer, right? And so, right here we see literally every 50 seconds that we've measured the concentrations of NO2, NO, and O2. Now, realistically speaking, is this probably possible in a lab? No. No, almost certainly you would have to measure one of these and then calculate the others from it. Now, right here we see that the NO2 is disappearing as time progresses. You'll notice that it disappears faster at the beginning, and then it starts disappearing slower. And that's because the reaction's getting slower as we go along. You actually probably would have already realized this. How do reactions take place? Well, you need NO2s to bump into each other normally, right? And so, if you have a lower concentration, they're less likely to collide, less likely to react, right? Okay, and so right here, what we see is that NO is being created as time goes forward. You see that? And here we see that O2 is being created as time goes forward. So these concentrations, which are our products, are going up as our time goes on. This right here is going down as our time goes on because it is making this. So right here, this would then be a plot of that same information. Notice right here is the concentration. Again, that is moles per liter. Another way of saying moles per liter is molarity. Right here we see time. This is literally just that time axis right there. And that's in seconds, of course, just like on our table. And so here we see each species. This is NO2. This is the reactant. I don't even need to look at the reaction to tell you that this is a reactant because we start with some of this, it goes away, and it makes the products, which are right here. They're going from 0, we didn't have any at the beginning, up to a larger number. If you look closely, you will see that these are a logarithmic / exponential relationship to each other. And what that is as this disappears, the reaction gets slower and slower. Eventually, you're going to have so little that they're going to have trouble even reacting. As we go and create more and more NO, NO2, we're going to have less and less that we can create. And so these are actually going to trail off and sort of even out here if we were to go further. But that's a topic for another portion of the course. Now, first we need to understand these average rates. So the average rate at which the concentration of NO2 changes over the first 50 seconds, notice that this average changes as we go into different time periods. So here we're looking at the first 50 seconds, from 0 to 50. If we were to calculate that, that's going to be the slope, but it'll also be the change in concentration over change in time. Okay? So we can literally just do the calculation of the change of concentration. The difference will be the concentration right here at time 50, which will be our ending, our state 2, minus time 0, because we're doing for the first 50 seconds, remember? So our first initial state is time 0. Our second final state would be time 50. And so this is what that means. This is the concentration of NO2 at time 50. And that's how you notate this. This right here is the notes telling you that it's at that time. This right here is your actual concentrations that you're looking at. Now, down here, because we're doing it for the first 50 seconds, the time has to be, well, 50 seconds. Has to be 50 seconds, which is our final state, right? Our state 2. Minus 0 seconds, which was our initial state, or state 1. And so, of course, we now substitute these numbers. They come from that table, or you could have taken them off the graph, but that'd be harder. And you plug these in. You will notice that this is going to end up being a negative number. And does that make sense? Every time you do a calculation, does that make sense? Well, NO2 is your reactant. It is disappearing. That means it is going down over time, isn't it? And so, yes, that makes sense. That is a negative. That's telling you I'm going down over time. I'm disappearing. This right here is in moles divided by liters seconds. Another way of saying that was this would be in molarity divided by seconds. That would just be another way of writing those units out. All right, so since the concentration of NO2 decreases with time, again, this is going to be negative. The concentration of reactants will always decrease with time. That's actually typically why we put them as reactants, right? Reactants are what we start with. They're what we mix in to do the reaction. Any rate expression involving a reactant will include a negative sign then. So hence, we get this value right here, which would be our rate. When we actually write this rate out to express that this is a reactant, what we should do normally is we should take the rate, set it equal to the negative value here. What that will do is it'll give us positive rates that we can just use for the reaction in general. Okay, and that's what we're saying is this reaction proceeds at this rate. And notice I said this reaction. I did not say that reactant, which is NO2, right? So I'm making a value that I'm using for the full reaction by getting rid of its sign, which is what I'm doing here. The rates are not constant. So if we were to do the rates for the first 50 seconds, the next 50 seconds after that, the next 50 seconds after that, and so on, what we would see is the rate of the reaction goes down. The reaction will get slower and slower and slower. because again, you are always going to consume your reactants. And so yes, in these reactions that only go one direction, notice this is not an equilibrium we're discussing right here, this rate is going to continuously slow down. All right, so the instantaneous rate. This is going to be the value of the reaction rate at a particular time. Does that actually help you out that much? No. No, the instantaneous rate is something that we have to do mathematically. It can be very useful. At certain points in the reaction, it actually becomes very useful. And it does tell you information about it. But it is a somewhat artificial number, okay? Because it is happening at an instant. I mean, think about that. How fast is a car moving at this exact instant? Which would be, no amount of time in time, which would be an exact moment of time. Well, it's not moving in an exact moment of time, is it? So, when you look at these, you're going to take the slope of the tangent line. So you'll take a tangent line like you see right here. That's what this is showing you. This is showing you an instantaneous rate. So we take that point right there in time. We take and draw a line through this to give us the slope of that point in time. You see that it should merge with this portion right around the time period. And then it will diverge from the actual curve as we go further out. Because again, the rates change over time. So that will then be the slope of that line that is tangent, the slope of the tangent line, if you will. And that's the figure that this is talking about, by the way. And so how do we figure out a slope? Well, the slope is always the change in y over the change in x. Of course, y is the concentration of NO2, so it's the change in NO2, over the change in time, which is the x axis. So that's actually very similar to the rate, isn't it? So the rate is actually equal to the slope of the tangent line at that moment in time. So that's actually true for all moments of times. And you'll actually see, if you look closely at those tangent lines, there are certain parts of that reaction that actually the tangent line matches up to that overall curve very well. And so you actually don't have, there are times where you can do the instantaneous rate and it will essentially give you the reaction rate for the first 50 seconds, okay? And we'll talk more about that in just a bit. So right here is actually the example you've seen before. We've just gotten a number from it. So there we go. All right, so let's consider the reaction of this reaction here, which is again that NO2 going to NO, NO2. So NO is going to be produced at the same rate NO2 is consumed. How do I know this? Well, they have the same coefficients, don't they? So that means every time I use up an NO2, I'm going to make an NO. Every time I use up 2 NO2s, I make 2 NOs. Every time I use up 4 of these, I make 4 of these. And so we know that these have to be produced and used at the same rate. So at 250 seconds, the slope of the tangent to the NO curve would be this value right here. And that means that this would also be a similar rate, the same rate, for the NO2. Because again, they're going to be the equal but opposite rates. Now, if we look at the slope of the tangent of the O2 curve, remember O2 does not have the same coefficient. What we will find out is this is a different value. Very similar, but it is different. So here we had 8.6 times 10 to the negative 6 for the NO curve. Notice that is a 2 coefficient. Here for the O2 curve, we find out that's 4.3 times 10 to the negative 6. Look at that. That's half, isn't it? That makes sense. Because every time you produce 2 of these, how many of these will you produce? Well, that has a 1 there, doesn't it? And so that means you would produce half the number of O2s you produce for any NOs you produce. So that means the rate has to be half, because every time you do this reaction, you produce 2 of these, 1 of these. All right. So again, the rate of the NO production is twice that of the rate of the O2 production in this reaction. So your rate of consumption of NO2 is going to be the same as the rate of production of NO. Notice the production consumption is actually telling you the negative and positive signs. Consumption consumes, goes down, that is negative. Production goes up, that is positive. Okay, so what we're looking at here is, again, this is going to be this right here. This is the consumption of NO2. That's going to be negative because it's going down. This right here is going to be the production of NO, and that is going to be positive because it is going up. When we look at the O2, that is going to be made half as often. So that is going to be made at half the speed. Now what that means is that this value right here, to be equal to these, would have to have a 2 in front of it to remove the fact that it is making half, right? And so what you see here is whenever you have a coefficient for the others, always goes in front of this, okay? So the 2 always goes above in the numerator when you are half. Another way of thinking about this is that when you're making half, when you're making a third, you always flip it, okay? And you'd always take the inverse. So if you're making half, you put a 2 in front of it. If you're making a third, you put a 3 in front of it. All right? This is probably the single most common mistake I see students making, is when they try to do these relationships, instead of putting the numerator 2, they will put 1/2 here for this being half. And they don't understand or forget that it needs to be the inverse. You're undoing that so it's equal. So the average rate of disappearance of ozone in this reaction right here, which is 2O3, which is ozone, going to 3O2, which is the oxygen gas, is found to be 9 times 10 to the negative 3 atmospheres over a certain interval of time. Notice we don't even mention how much time this is. We don't care. What is the rate of appearance of O2 during this interval? So again, you're starting with ozone, right? You know ozone. And so you're going to then have to put this value equal to some sort of oxygen value. So the easy way to do these, in my opinion, is to just take this value right here. That's going to be times. This then is going to be divided by in front of the concentration of O2 over the time, right? And so when you're going and getting your actual value here, this is going to be, again, okay, so, all right, so what you want to do here when you look at this, excuse me, is, again, you are going from ozone. This is the number for ozone. This, what we're trying to get is the number for oxygen. And so what you're going to do is, there's 2 ways of thinking about this. You can write out the rates. So you could write out the bracket O3 over time, right? Equals the bracket O2 over time. And what you would do then is you would put this number on top over next to the O2 one. And so it would be 2/3 O2 over here on the right. And then you substitute these numbers in. So this would go on the left with the ozone. You would then multiply over 2, or multiply over the 3, and then divide over the 2, which would give you 1.3 times 10 to the negative 2. Now, that is a totally valid method to do this, and for most people that find math very comforting and formulas very comforting, that's the way I would recommend to do it, okay? Some people are just more comfortable with formulas. and stating those formulas over and over so they can work through them. Now, if you're okay with using a little bit of thought and logic to make this problem easier, then you are converting from O3 into O2, right? And so you can do this like a conversion. So right here we have the ozone. So when we're converting something, we always have to divide it by the ozone number, right? So we can get rid of ozone. Remember, you always take, if you're in moles on the top in the numerator, you divide it by moles on the bottom, right? And that means that you get rid of the moles. And so what we can do here is we're going from here, we need to get rid of the O3 portion of this, right? So we divide by the 2, and then we're going into the O2 portion, so that needs to be in the numerator. So we multiply that by 3. And again, I'm just using logic of the same sort of logic that lets me go moles to moles in here, lets me go molarity into molarity in here. I'm just realizing that that same pattern exists here because all of these are moles, pressure, molarity, etc., right? They have the same pattern. And so yes, you can make this sort of problem very, very short by, again, you just divide by what you're going from and you multiply what you're going into. There you go. Okay, so rate law. Chemical reactions are reversible. Most chemical reactions are going to be reversible. The ones that are irreversible typically actually are due to the fact that the gas escapes and you can't get back. That's the majority of irreversible reactions right there. So NO and O2, as they accumulate, they can actually do the reformation reaction. They can reform to make NO2. Remember when I said we're going to go on to another section where we'll have the reaction going in the reverse? Here it is. All right, so as you make O2 and NO, these are going to start reacting. There'll be larger and larger concentrations or pressures. They'll start reacting with each other, and they will start forming the reverse reaction, which is going right here, O2 plus NO to yield NO2. So when gaseous NO2 is placed in an otherwise empty container, the initially dominant reaction will, of course, be NO2 going to NO and O2, which is because there is none of this at the beginning. All you have is this. So you don't have any of these reactants, if you will. You don't have any of these products at the beginning to go in the backwards direction. But what happens as this reaction progresses? Well, as this reaction progresses, you're going to have more and more NO and O2. And that means this reaction will start catching up. So the change in the concentration of NO2 depends only on the forward reaction. Reverse reaction becomes important as you gain enough products to accumulate after a period of time. Remember where I said that this graph would go on way back in the beginning when we were looking at these curves for the reactions? This is what we're talking about. This part right here is that side portion of the graph we did not show before. So the expression to be used if the reverse reaction is to be neglected, we don't have to worry about the reverse reaction because we're looking at before the reverse reaction could happen, is this right here, which is the rate expression, if you will. This right here, or the rate law equation. This right here is going to be the rate, and again, that's that same rate we talked about up here, where it's the change in concentration over change in time. It's the same thing. That's that rate. This is going to be equal to a rate constant, which is lowercase k. Careful that you don't put uppercase K. Uppercase K is actually a combination of lowercase k's. That's what that actually stands for. So when you see an uppercase K, that's going to be several lowercase k's multiplied and divided into each other, or even subtracted occasionally. Mostly multiplied and divided though. And right here, this is then going to be the concentration you always state rate law equations in terms of the reactants. You never state them as products because, again, this is if the reverse reaction is to be neglected. So by definition, we're only concerned with reactants. And then this is going to be to the power of n. N will be some sort of integer, okay? It could be 0, 1, 2, 3. Those are the only really possible n's. If I made up data, somebody would have to make up data. It couldn't be real data. If you start getting n 4s, 5s, 6s, that sort of thing, okay? These n's right here, they oftentimes, the first one will be n. If you have more of these, they may be n, m, o, etc. These right here are called order of reaction. And so with respect to NO2, this would be the order of the reactant. So again, this would be the order. This would be the species we're talking about. So with respect to NO2, it has an order of blah. All right, so the concentrations of products do not appear in your rate laws. The reaction rate is being studied under conditions where the reverse reaction does not contribute to the overall rate. So that's actually part of the definition, and thus you can never have the products showing up in these rate laws. That is a violation of the concept. The value of the exponent n must be determined experimentally. This cannot be written from the balanced equation. This n value is not, I repeat, capital letters, not the coefficient. Okay? It doesn't make sense why I'm stressing that so much right now, but once we go on to the next chapter, you're going to realize, my God, I'm going to get this confused. And so what you need to do is right now, break yourself of any thought that this n number here, these order of reactant, is a coefficient or related to the coefficient in any way. So the definition of the reaction rate in terms of consumption of NO2 could be done like so. So right here we have the reaction rate. Here we have the definition of the reaction rate, which again would be the negative change in concentration over change in time. This is also equal to K, which is a constant, times the concentration of NO2 to its order. These are all equal to each other. So the definition of the reaction rate in terms of the product would be so. So here we see this is a modified rate because we're doing it in terms of product here. And this right here is how you would express this reaction rate in terms of product. And right there we have again the rate law. Notice it is still written in terms of reactant even now. So this is K prime because we're actually expressing the rate in terms of production here rather than consumption. And then this will be multiplied by NO2 concentration to its order. So as 2 moles of NO2 molecules are consumed, for every O2 molecule produced, the rate of the consumption of NO2 will be equal to 2 times the rate of production of the O2. Another way of stating that would be that the K right here would be equal to 2K prime here. So the value of the rate constant actually depends on how you define your rate. So if you define your rate as consumption of NO2, then your rate constant is just 1K. If you were to define it based upon the production of O2, then you would have to see that it was 2 times K prime. It would actually be a different rate constant. So these are the types of rate laws. We have the differential rate law, and that's going to express how the rate depends on the concentration of the reactant. We then have the integrated rate law. This will express how the concentration depends on time. The type of rate law used is going to depend on what types of data are easiest to collect. Literally, we just have two different types of rate laws that we've worked out the math for and simplified. And depending on whether we can, measure the amount that's made, or measure the amount that we are using, or what's easiest to figure out the data for, that's the one we choose. That's it. There's nothing else magic about that. It's literally what is the easiest to collect data for. All right, so right here we see a concentration of N2O5 solution in this column right here. And so we have our concentrations. That's our reactant, so it's what we start with. You see the concentration slowly goes down over time. At first, it's going down pretty fast, and then it slows down as we go further. Right here, we have our time. And again, this is at 45 degrees Celsius. That exact number isn't really that important here. It's just so you know that it's at that temperature for the entire thing. So, how can we get our differential rate law for a reaction? So let's consider this reaction. We have our N2O5, that's the reaction from the top there, by the way, and that's going to the NO2, which 4 NO2s are being made every time 2 of these break apart. Every time 2 of these break apart, we know that a single O2 is made. In this case, since we start with 0, none of the product, the reverse reaction has to be negligible for this first portion. So the evaluation of reaction rates at concentrations of N2O2 of 0.9 molarity and 0.45 molarity would yield the following data. So what we see is at 0.9 molarity, we see that the rate would be 5.4 times 10 to the negative fourth. At 0.45, we see that is 2.7 times 10 to the negative fourth. You will notice that in this case, at half concentration, we're seeing half the rate. And so right here, this is a plot. This would be how the easiest way to do these instantaneous rate laws, typically by plotting them and using the curve to draw in these tangent lines. This is one of the ways you can do this, of course. There are others. So right here we have our plot of concentration. We have our instantaneous rates being drawn in, like so, and these would be then the tangent lines, which we take the slopes of, and how we found those rates. Remember, the slope is related to the rate in this case, is the rate in this case. So when our N2O5 is halved, the rate is also halved. The differential rate law for this reaction is thus, well, our rate equals our change in concentration over change in time. Since this is a reactant that's going down, it needs a negative in front of it. It will be equal to the rate constant times the concentration. And in this case, this is going to be the first order. So the order of a particular reactant must be obtained by observing how the reaction rate depends on that concentration. Since this is a linear change in the concentration versus the rate, this has to be an order of 1. If you change the concentration and it didn't change the rate, we'll get into those, but that would be an order of 0. That means that this doesn't matter. So for the rate law of the decomposition of N2O5, we see that it's equal to the change in concentration over change in time. It would also be equal to the rate law right here, which is K times its concentration, and that's it. By the way, if you have an order of 1, you don't actually have to put that, because anything to the first order or anything to the first power is itself. It doesn't change anything, mathematically at least. The method of initial rates. So the initial rate, the instantaneous rate determined just after time 0. This is typically the easiest instantaneous rate you can determine. Several experiments can be carried out using different initial concentration of each of the reactants. The initial rate can then be determined for each run. And notice that these are going to be called runs so that you can differentiate them from the fact that you're running an overall experiment here. Okay? So the results are then compared to see how the initial rate depends on the initial concentrations. So what you'll do is you have right here, you have your experiment which has run 1, 2, 3, 4. These have, so for run 1, you started with 0.1 molarity of BrO3 minus in this case, which is this reactant right here. 0.1 molarity of Br minus, which is this one right here, and 0.1 of H plus. All right, so you are then going to take and you would then figure out how fast that initial amount is consumed. And so this would then give you your initial rate, which is this right here. This is going to be the rate of the reaction for this initial concentrations right here. Okay? Now, that means that if you were to look at the rate law, this would be the rate right here equals K, which we don't know, which is fine. We don't actually need it. Times some sort of concentration of BrO3, so this concentration right here, to some power, which is called its order, right? Times the concentration of Br minus, which is right here, to some power, which is called its order, which is the order with respect to Br minus. And times the concentration right here with an order that we will have to figure out. And so what we're doing here is when we look at these concentrations, if we're going to gather this data, what would you expect to see is that you should have, for each set of data, you should have a baseline, which is right here. That's number 1 in this case. That's simply something so you can compare it to the other sets. Then for the other sets of data, one concentration and only one concentration should change. Typically you would double, so it's easier, or half. So in this case we see BrO3 right here has been doubled from run 1. And we see that that's the only change in concentrations. If we look down here, we see that run 3 we have actually doubled both BrO3 minus and Br minus. So when we compare these, what we should do is we can compare them only to run 2 and 3. Because you see run 2 and 3 differ in only one place. If you want to find out what's going on here in run 4, notice this only changes one data point from run 1. See that? You've doubled exactly one of the reactants. Now, why do we want to look at something that only has one data point changed? Well, think about it this way. If I compare run 1 and 3, what I'm comparing is not just the effects of this concentration, am I? I also then have to take into account this concentration changing. But if I compare run 2 and 3, the only concentration I have to worry about is this one right here. It's the only one that changes. All these other concentrations, their effects, do not change. They're the same between 2 and 3 because they have the same concentrations except for one set of concentrations. That's it. So every time you work on these data, you should always find where it changes one thing at a time. And this is just good science. Honestly, I would be surprised if the majority, if I asked you, okay, what effect does adding more milk have on to making a cake? What would you do? Would you change the amount of every ingredient every time? Or would you just change the amount of milk? You change the amount of milk only, right? And that would tell you what effect it has on baking a cake. So again, this is just good experimentation, good science. We change one thing and see what effect that has. All right, and so right here, if you look, you will see that when we changed only Br minus, we get a doubling of this rate. So Br minus, when you double the concentration, it doubles the rate. What that means is they are proportional. I want you to sort of get used to looking at data and evaluating the data itself. Part of the reason I'm trying to make you get used to this is, number one, it's just a great method to expanding your critical thinking skills. But part of it is also the fact that you can save yourself a tremendous amount of time and effort on these problems by just understanding the relationships they have to have. You can cut out entire portions of these problems. So I'm up front showing you how to cut out portions of the stuff I'll end up doing with you in just a minute. But you'll see that they were entirely unnecessary. So right here we see doubling the BR minus doubles the rate. Since they're proportional growth, they're the same, doubling. That means they have to be the first order. Now, right here, if we then look at this one, so this one right here, what would we have to compare run 4 to? Well, the only one it would make sense to compare to is run 1, because you've only changed H plus in that case. Every other thing, you've changed two items, two concentrations. You won't be able to figure out what effect that has. There's too much data. There's too much changes. It won't help. So we compare run 1 and run 4. And we see that this versus this, by the way, notice this is a 10 to the negative fourth. So this is 10 times this value right here. So this is actually an 8 versus 32, right? So where would you get an 8 versus 32 sort of relationship? Well, that is a 4 times relationship, right? What that would mean is that 4 times 8 would be 32. And where am I getting this 32? Because 10 to the negative 3 is 10 times 10 to the negative 4, okay? Now, that means for doubling the concentration, we get 4 times the effect. Hey, what is 2 to the power of 2? Well, that's 4, isn't it? And so that is the order of 2. That is an order of 2. Doubling concentration would have 4 times the effect. That means it is in second order with respect to H plus. All right, now let's look at this one. It runs 1 and 2. Again, we look across and we see this is the same, this is the same. So the only one that changes is this right here, which is the concentration of BrO3. Now, we see that we're doubling that concentration. And that doubling of concentration has the effect of, again, doubling this. You see that? And so when we double that concentration, we're doubling the rate. Well, if that's doubling the rate as doubling the concentration, that means that's proportional. That's double, right? Same, doubling 2 times. So that means that this would also have to be first order. So you notice that I can very quickly, if I didn't have to speak out and explain every single step here, I actually rapidly figured out the orders without doing any real math. I just looked at what it did and said, hey, this is the same, doubling is doubling here. And so that has to be first order because it doesn't have any exponential power. This right here is to be, well, you're going doubling, is giving you a 4 times effect. And so that would have to be second order. Okay, so let's determine the orders. We'll do it mathematically this time. And then we're going to determine the value of the rate constant. Alas, these problems always have a little bit of length to them because you always have to get the orders before you can get the rate constants. Okay? So the general form of your rate law is always going to be like so. So right here we have a rate law. It's always going to be rate equals small k, the concentration of the first reactant to its order, the concentration of the second reactant to its order, concentration of the third reactant to its order. And you would keep putting in each reactant to its order, okay? Note that we have 3 reactants, so we have to have 3 concentrations to their orders. All right, so the first part, we're going to have to figure out the order that is denoted here as n. So what we do is we're going to take runs 1 and experiment 2, so run 1 and 2. We will substitute those in and we'll divide one by the other. Now, you probably haven't done this in math in quite a while. Typically, when I teach this class, I find out most people haven't done this in years, and essentially, when they look at it, they go, "Oh, yeah, I remember that," because it's actually not hard. But most people, at first, when they look at this, go, "What the hell did you just do? What is this?" Okay, so what we have here, we have this equation right here on each of these lines. So see, this is rate right here for the first run. It's equals to, that's the rate that we got from that table right there for the first run. That's equal right here is the K right there. That's the concentration from the first run to the power of n, because we don't know that, times the concentration from that first run of Br minus to its power order, which we again don't know, times its concentration from the first run of H plus from that table again, and this would be again to an order we don't know. And so this is actually why we need these values to match up. This is the math behind that. So again, this would be rate 2. This is the second run. Its rate is right here from that table. Again, K, the concentration from the second run for BrO3 minus, again, this is all from this table right here, okay? Don't forget that. Okay, and then it's the concentration, of course, Br minus is right there for the second run. H plus is right here for that second run. Again, we do not know any of these orders, N, M, P. They don't matter right now because we don't know them. We have played a trick that allows us to not care. So right here, what do we have? Well, we have this 0.1 divided by 0.1, don't we? What does that mean? That's 1, isn't it? Anything divided by itself is 1. Anything divided by itself is 1. Well, if you put 1 to the power of anything, what do you get? Think about it a little bit. You get 1, don't you? 1 to the first power, 1. 1 to the second power, 1. 1 to the third power, 1. 1 to the 0th power, 1. So we have made this 1 to an order we don't know, but it doesn't matter because we're just multiplying by 1 no matter what we do. And so that's why we need these all to be the same values, okay? It's why we can only have one of these values being different between these two runs we use, is because that one that's different, that will stay. The rest of these we can just cancel out, because again, multiplying anything by 1 is itself. 1 to any power is always 1, so these won't matter anymore. K divided by K also won't matter anymore, will it? K divided by K, anything divided by itself is 1. Anything multiplied by 1 is itself, isn't it? It doesn't change it. And so here we see that we get, this is 2 times this value right here, which gives us a 2. These concentrations right here are the only ones that end up mattering because they're not the same. And that means 0.2 over 0.1. And that is going to be the power of n. And so what we see is this will be 2 equals 2 to the power of n, our order that we don't know yet. But the only way this 2 could equal this 2 is if this was the first order to the power of 1. By the way, if you wonder how you actually do this problem, how you would actually put this in the calculator, frankly, I would never put something like this in the calculator, okay? Typically, I would just take 2, and if I don't know that this is to the first power, I'd start plugging in powers. I'd literally take 2 to the first power. Oh, that's 2. 2 to the 0th power, you should know that's always 1. Anything to the 0th power is 1. And if it wasn't 2 to the first power, then you'd put 2 to the second power, which would be 4. You go, oh, that's not right. If you actually want to do the math to do this, you would take a log of both sides. Log would cause this value right here to go out in front of it. So you'd put n log 2. And this side would have log 2. You would then divide this log 2 over, leaving you with n equals the log of 2 divided by log of 2. And that's how you would do that problem if you were trying to actually do that math. Anyways, hopefully you can see that 2 to some power, that power has to be 1. Hopefully you're that comfortable with exponents at this point. If you're not, I highly recommend you review, because that's a serious math weakness. All right, now let's determine the value of m. So again, we're going to use the results from 2 and 3 in this case. Why are we using 2 and 3? Well, that's because they have the same values for all but one concentration. And so we plug in, again, 2 and 3. Experiments 2 and 3 runs 2 and 3. And that gives us this rate over this rate, rate 2 over rate 3, which will give us these concentrations. Again, K cancels. This will cancel again. This right here is going to be the one that goes down, because they are different concentrations. And this right here is again going to cancel. By the way, if you plug these in and you get something where you have 2 that do not cancel, I would not do that. You should go back to your damn table and get the correct ones, okay? You messed up. But there is a trick you can play. Because we know the value of n at this point, which is 1, we could have plugged in this n right here. You could do that. You could actually solve for that. It would make it a lot more difficult. It'd be a lot more work, but it is possible, okay? Just letting you know that it is possible to do a different route here. But again, I would do the correct way. It's just easier. Now, again, this is going to be 2. This right here divided by this is 2. Again, this concentration divided by this concentration is 2 again. And so what we find out is, again, 2 equals 2 to the m. And m in this case has to be 1. So we find out that this is also first order. And so our next one, our final one we're getting our order for, we do run rate 1 versus rate 4, or run 1 versus run 4. We plug the rates in here. Again, the concentrations each get plugged in. Again, you see that these are the same, these are the same. This one right here is the only one that's different. So again, we have 2 times here. And that's that. 2 to the power of p. This right here would be 4 times this one. And so that gives us a factor of 4 here, 4 times. All right, and so you end up with 4 equals 2 to some power. And we go, well, to get 4, 2 would have to be the power of 2. And so this is, of course, second order. Now, notice that that took a lot of work, a lot of writing to get something I just look at a table and can get. And again, you can look at a table and get. That is not magic. It is not actually that difficult. All it takes is a little practice and thought. All right, one of the questions I usually get at this point is, Dr. Clausen, why do you put this value up here and this one below? Why do you put rate 4 versus rate 1? Why isn't it rate 1 versus rate 4? And the answer for that is, I did that so I get a whole number, so I get 4 instead of 1/4, right? Do you have to do it that way? No. No, you can do it the other way. It'll be fine. If you did it with rate 1 on top, and you did everything for rate 1 on top, and then you do rate 4 on the bottom, it'll be fine. You'll just have to work in fractions, okay? Which is a pain in the butt, but it's not something that is impossible to do. It's entirely doable. It's just annoying. So typically I try to keep the larger values on top, okay? All right, so the overall reaction would also have an order. You figure out the overall reaction order by adding up all the individual orders. So in this case, we had first order, and second order. And so our overall reaction order is fourth. It's fourth order overall. All right. So our rate law for this reaction is going to be in this form here. And so we have the rate equals K times the concentration of Br3 minus to its first order, which you don't have to write because 1, anything to the power 1 is the same thing. To the times the concentration of Br minus, again it's first order, so you don't have to write anything. Again, then it would be times the concentration of H plus, which is your third reactant, and this is second order, so we have to write a 2. All right, now you should always go ahead and write out your rate law before you try to figure out your rate constant, because you're going to have to plug values in to solve for it, okay? It's just like writing out your equation before you plug in the values, right? So all you have to do to figure out K is literally take any of those experiments, any of those runs. 1, 2, 3, 4, does not matter at all. I typically take the first run just because that's usually the easiest one to do. And so I literally just plug those values in to my rate law for this reaction right here. And so I have the rate in that table, plug it in. I have my concentrations, I plug each of those in, which are these values here. There's your rate. That leaves K. Now I do the math. So I multiply these, I take the power to that one, I multiply it in, then I divide those over, that's it, done. So here we see the values plugged in. I plugged in each of these values from the table for run 1. Then we do the math, and again just do this stuff first, so this, times 2 of these, times 0.1 times 0.1 again, and that gives you this. We're then going to divide that over, which is what we're doing here, which will give us K equals 8 liters to the third over moles to the third times seconds. How do I get this value right here? Well, this right here is my rate. My rates are always molarity per second. So moles over liter seconds. There's another way of writing that. So that means that the K has to get rid of all but one of these molarities from here. So whatever I have here, I'm going to always end up getting rid of all but one of those moles per liter, and that means it's moles per liter cubed. See that? You're having it so it gets rid of all but one of those. And then divide by seconds. Now, again, if you just put your units in and do the math, you will get the correct units at the end, okay? Oh, let's do a reality check. Every good problem solving in science should always have a little bit of a reality check. So let's verify the same value of K can be obtained from the results of other experiments. So what we should do then is we should go ahead and plug these in, the concentrations times that K value we come up with, and get these rates for the other runs. And if you do that, you should find out that yes, this value of K is correct. It will get you those rates. Okay, so now we're going to do a couple quick join-in questions here. So for reaction A plus B yields products. Again, we don't really care what the products are because all the rate laws are always in the reactants. The following data was obtained, and so here we have our experimental results. Notice that in these experimental results we have our rate right here. Remember, initial rate can be used when it's that first part of the reaction. And this right here is our initial concentrations. By the way, this 0 on the bottom here, that means at time 0, or at the beginning, you had these concentrations, okay? And so what we see here is this is run 1, run 2, run 3. It's just reorganizing the data in column format. All right, so our rate for this, where it is 0.1 versus 0.2, is 0.03. That's how fast it is. When we're talking about it being 0.2 and 0.2 here, which notice that 0.2 matches for B, meaning this is the change of A and how it affects the rate. So when you double A, it doubles the rate. Can you see that? That is 0.03, that's 0.06, that is double. Your concentration of A doubling, that has doubled your rate. And so that would be an exponent of 1. That would be first order, because doubling the concentration doubles the rate. That means that it would have to have an exponent of 1. 2 equals 2 would have an exponent of 1. Now, this right here then, what we need to look for is now we need to look for a change in only B. Again, you need to only change one factor to find out its effect on concentration. And so we look here, let's see, we used run 1 versus run 2 to figure out A, didn't we? Because B did not change. So we can look here, hey, run 1 versus run 3, no, they both change. I can't use those two versus each other. How about run 2 versus run 3? Hey, A stays the same, B changes. That's perfect, that's what I need. And so what I'm seeing here is I'm seeing that when I take B and go from 0.2 to 0.3, it does not change at all. And so you may feel like you have to do some sort of math here, but you don't. If we change this amount here, the concentration, and it has absolutely no effect on your rate, the only way that could happen is if it's zero order. And the reason for that is anything to the power of 0 is always 1. And that means it doesn't matter what numbers you put in for the concentration of B. It always has a times 1 for everything else. It always has no effect on your rate. Okay? So any change in concentration of B has no effect on rate. That means that we don't need to include B into the rate law. Or another way of thinking about it is that concentration of B, it'll be to the 0th order, which means to the power of 0. The power of 0 gives you 1. You don't need to write 1s into equation, right? Anything times 1 doesn't change. Anything to the power of 1 doesn't change. You don't need to write them. All right, so that means we have to have A here. So you have the rate equals K, that constant, times the concentration of A to the first order. The concentration of B would be to the 0th order, meaning we don't have to write it. Okay, and there we go. All right, so the integrated rate law. You may have noticed that the rates can actually be rewritten. There's quite a bit of formula there, right? And there's powers. So this is going to be used to express the concentration, the reactant concentrations, as a function of time. This is the big way we can then spin how we're going to look at these to make it easier to solve in cases where we want them as expressions of time. Where we have time essentially is what we want to deal with. Notice that before we're dealing with concentrations and rates. All right, so this right here is going to be our basic formula. So rate equals the change in concentration of a reactant divided by the change in time. This is negative because it's disappearing, right? This also equals K times the concentration to the order. So for a first order rate law, this order would be 1. And so this right here would be that expression that we just looked at. So this would be an example of the rate law for the decomposition of dinitrogen pentoxide, which is this compound here. This is referred to as a first order reaction because the entire reaction is first order here. The rate of formation of products increases with the increase in the concentration of the reactant. This tells you the more of the N2O5 you have available, the faster the rate. So, and by the way, how do you know that? Look here. The more concentration you have available of this, the higher this number is, the higher the number in the rate, right? There you go. So the first order reaction, we can convert this into an integrated rate law. Now, anybody that's had calculus or goes on to calculus, you'll actually recognize this, okay? We don't require a calculus for this course, so I'm just going to wave my hand. Imagine my hand making a magic waving gesture, and ta-da, it's been integrated, okay? So this is then the integrated first order rate law. So this is going to express the concentration of the reactant as a function of time. So this is our integrated rate law for first order reaction. And this is natural log. That's the natural log as in the power of E. So E to the power of would be the opposite of this. Natural log on your calculator is how you do this, which is ln. Do not confuse this for the log log, which is base 10. Okay. Natural log of our reactant equals negative K, which is again our rate constant, same rate constant as before, times T. This is a single time, so you can now do this in terms of a single time on that graph, okay? You don't have to have a range of time or initial time only. You can just do it for any time now. And that's what this is so useful for. We've now done this as an expression of time. Plus the natural log of your initial concentration. So the concentration at time 0. So this would be what you start with. This right here is the concentration at this time. Okay? So let's say we put 50 seconds in here. This would be the concentration at 50 seconds. This will always be the concentration at time 0. It doesn't change. These are both actually constants, K and this, just like a linear equation. If you're thinking about this, if you blur your eyes a bit, you should have seen that this would be a y equals slope times x plus b, which is your y-intercept, right? So let's consider a reaction with our following rate law. So again, this is just that rate law right here. Rate equals K times the concentration of reactants. It's the first order in this case. This integrated first order rate law only works for first order. You'll see that we'll do the integration for 0 second, and they will be different. All right, so this is the natural log then, equals of the concentration of A at that time period, equals negative K at that time. So these are the same time, remember that. So if this is time 50, this is 50. This is time 100, this is time 100. This is always in seconds, by the way, just like these units are always in seconds. Or if these units are in minutes, this would be in minutes, okay? These need to match up. The units for K always dictate what T is. This is plus the natural log of your concentration reactant at time 0. Notice that this cannot change during the time and reactant, or the reaction. This is what you started with. What you start with never changes. Doesn't matter how much I spend of $10, what I started with, $10, is what I started with, right? So the equation expresses the influence of time on our concentration of A. The initial concentration of A and the rate constant K can be used to calculate the concentration of A at any time you want to find it out. So any time you want to know, whether it's time 90 seconds or a billion seconds, does not matter. This equation will allow you to figure out the concentration of A based on that rate constant and the initial concentration. The equation actually does match up, of course, to a linear equation, which is in the form of y equals mx plus b, Again, your y would be the natural log of your concentration. X would be time, which, by the way, you can plot, of course. The plot would be natural log of A, your concentration, versus time, which would be in the X. And M, your slope, is negative K, which is a constant again, remember that. B is your y-intercept, which is, again, natural log of your initial concentration. So for your first order, the natural log of A versus T always gives you a straight line, a linear equation, a straight line. So it'll always give you something that is a straight line. All right, so the equation can also be expressed in terms of the ratio of A versus A0. So what we've done is we have subtracted over the natural log of A. We actually subtracted over KT and subtracted over the natural log of A so that we could flip them and get everything positive. Anyways, you can try that out sometime if you're feeling confused about the math. It's basic mathematical principles. All right, so this gives us, if you take a natural log subtracted by another natural log, you take the things inside the natural log and you'll take the positive one and divide it by the one that's being subtracted by, which is what happened here. So this right here would actually give you these as a ratio. Notice that this ratio is for the time 0 divided by your concentration at this time. So this number inside of here is going to be a maximum of 1. So you could have what you started with, which would be this at time 0, right? I haven't used any. It's at time 0. It's what I started with. This value in here would be 1. If this is half, then this right here would be 1 over 1/2, which would be 2. If this was 1/3, this would again be 1 over 1/3, which would be 3. And so on. So let's calculate the N concentration of N2O5 at 150 seconds after the start of this following reaction. So we go ahead and use this information that we were given before in the table. So right there we see that the concentration is 0.05 at 100 seconds. The concentration at 200 seconds is 0.025. So the formula required to calculate after 150 seconds would be this right here, because this is first order. That's because it has halved in these 100-second time periods. If you look here, you'll see that it's halving repeatedly every 100 seconds. So 100 seconds later, halved. 100 seconds after that, that halved again. 100 seconds after that, this halved again, and so on. Okay, so this is first order. So we can then plug our values in. So T is going to be 150 seconds. K will be the rate constant that we would have to get experimentally by plugging these values in. And then the time 0 is again just at time 0. T equals 0, which is at the top of that table. So we plug those values in, we do our math, and we get our value right here, which is negative 3.343. So the value of N2O5 is not halfway between these two values here. This is before the anti-log. If you don't remember what an anti-log is, in this case what you would do is you would just take, because we're having to undo this, right? See this log right here, natural log of?
we're having to undo this. The easiest way to do that is to take e to the power of negative 3.343. And that would be your anti-natural log. By the way, this anti-log right here, this is actually the wrong symbol, if you're curious. Because this is a natural log. This should have been ln, not log. Anyways, so this is our final value here. You can see that that's not halfway between these. That's because this is a logarithmic relationship. It's not linear, it's logarithmic. And so yes, this is not halfway in between. It's a bit closer here. So yeah, you don't really get halfway in between these things. That's something you need to understand and take note of. Typically, I would just do the math. It's easier that way. So don't forget how to take an anti-log, by the way. If you don't remember how to do anti-logs, you should really work on that a bit. That's one of the actual places that I find is the two places I find to be the biggest failure points for students on these problems is number one, they just don't understand the conceptual part of it, and they have not learned the conceptual part, the jargon, the understanding of what's being talked about here. Because they just haven't went through the first part of the slideshow or went through the chapter. The second part that I find is a big problem for most people is the math. A lot of people just did not remember and don't remember how to undo logs or how to do anything with logs, really. They just blank. And so again, to undo a natural log, you would take e to the power of, and then you would take this number here. And that would be your anti-log, anti-natural log. All right, so let's talk about half-lives. Half-lives of a reaction. Another way of saying half-life of a reaction is T1 half, again, half time. This is going to be the time required for a reactant to reach half its original concentration. Notice that is, again, the time that would take you to reach half of the original concentration. That's not half the time you put into something, it's half the time, it's the time it takes to half your concentration, okay? Consider the general reaction, A, going to products. If the reactant is first order, then with respect to A, then we see that this right here is that relationship that we looked at before, the integrated rate law rearranged, with time on one side and concentration on the other. So if half of our concentration is gone, that means that A would equal half of the initial concentration. Okay, so if we plug that in, we would find out that we would get natural log of 2 equals K times the half-life. And this, again, term is the half-life. Again, by definition, half your concentration is gone. Or by another definition, same thing, the glass is half full means glass is also half empty, right? So half of your concentration remains, or half of your concentration is gone. So again, this is the half-life right here, T1 half. So if we substitute the value of natural log of 2 and solve for time 1/2, we can get this right here. So what this is this value right here is natural log of 2. Personally, I remember this as natural log of 2 because I just have trouble remembering numbers like this. However, the half-life for a first order reaction is always the half-life equals 0.693, or natural log of 2, over K. And what this does is it gives you a very easy way to find out half-lives. And we can actually figure out time based on certain things half-lives. We'll get into it later on in the semester, but this is how you do things like carbon-14 dating and all that sort of stuff. So the equation 12.3, this can be used to determine the half-life if we know what K is, or K if we know the half-life. So for example, we actually, on that previous problem, it would have been very, very easy because we knew what the half-life was, we knew the time it took to get half concentration. We could have just plugged that into this equation right here and gotten K. And that would have been much faster and easier than doing all that work we did before. So for a first order reaction, half-life does not depend on your concentration. Your concentration will not change your half-life. So right here we see an example of this. Here we're seeing our concentrations half each time. This is halving. This halves again. This halves again. This would be your first half-life, second half-life, third half-life. And so you have 1, 2, 3 half-lives occurring. Your half-life is 100 seconds. It takes 100 seconds to half each time in a first order reaction. And so again, this would be your ratio of concentration showing you the halving each time. Okay, so this would be plotting these concentrations versus time. And so what we see is that each half-life we will have our concentration after 100 seconds each time for this. And that will keep happening over and over and over, okay? You will see that each halving is a smaller and smaller number. You see that? That each halving is smaller and smaller. And this is because half your concentration is going down, right? And so half of it keeps going down. So a certain first order reaction has a half-life of 20 minutes. Calculate the rate constant for this reaction. How much time is required for this reaction to be 75% complete? Okay, so this is funny. B is actually faster and easier to do than A. And you'll find that out quite a few times, that because if you understand half-lives, the more information they give you, the less work you have to do. Okay, so if it's 75% complete, what does 75% gone mean? Well, 75% gone means you're left with 25%, doesn't it? Okay, so 25% is half of a half, isn't it? And so you would expect the amount of time required for this reaction to be 75% complete would for you to go through 2 half-lives. For it to half 50% and then half again, which would be 75% completion or 25% remaining. And so that 2 half-lives would take you 2 of the half-life, which would be 40 minutes. 2 times 20. Anyways, let's go ahead and do this the full way with all the math so you can get a little practice, right? So solving your equation for K gives you this value right here. And so what we do is, again, this is just the natural log of 2 over the half-life equals K. We plug in our half-life. We have natural log of 2 there. This divided by this gives us a K of this right here. 3.47 times 10 to the negative 2 minutes to the negative 1, which is that right there. All right, so B, well, you can, of course, do it logically, and it's so much easier to do it logically, like I showed you at the first screen. So 75% complete means that you've consumed 75%, leaving you at 25% remaining. We can, of course, also plug this in to our integrated rate law. So what we have here is we have 25% remaining. How do we calculate that? Well, we take the A at that time we're talking about, divided by the initial amount, which would be all of it, 100%. And that's times 100%, right? And that is how we figured out percentages. So we solve for that, and what we find out is this value, a over a0, equals 0.25. And so if we flip that, we can do the inverse. The inverse of that would mean 4. Another way of saying the inverse of this would be to flip it. So 1, everything is divided by 1, okay? So everything can be considered divided by 1. We can flip it for the inverse. That means 1 over 0.25. That would be 4 times, right? Another way, of course, is this is 0.25. That's a fourth of something. So the inverse of that is 4. Right here, then, we could plug that in. So we take, again, our integrated rate law. We plug that number in. This is that a0 over a, which is the inverse here, which is this one here. That is 4. So we have the natural log of 4 equals kt. This kt is right there's k. And so we have it times t. We then have to solve for t. So we take the natural log of 4 and divide it by 3.47 times 10 to the negative second. And that will give us 40 minutes. You will notice that this was a lot more work to get the exact same answer because it pays to be able to think something through. Okay? You ever heard the saying, work smarter, not harder? This is an example of work smarter, not harder. If you understand what you're talking about here, if you understand what we're doing, then you can vastly reduce the amount of work you need to do. Okay, so the alternate way here, in case you forgot how I did that, is spelled out here in the slideshow, and of course you can go through that method. The second order rate laws. Okay, we did the first order, now we're on the second order. And so the rate law for your second order is going to be, well, it's going to be rate equals k times the concentration to the second power, which is our second order here. So the integrated rate, second order rate law has this form here. And that's, again, I'm hand waving magic calculus integration, okay? Once you go through calculus, you could give this a try. But at this point, if you ever wanted to do something like this, that would typically be something you do in physical chemistry, okay? Physical chemistry 1, which is thermodynamics. This is not something we would do here in general chemistry, which is, considered freshman chemistry. Now, this is the integrated second order rate law. This would be 1 over the concentration. Again, that's for that time. Equals kt, again, time, plus 1 over the initial concentration here. You will notice in this case that we have a concentration component to this. So as you change the concentration, as your reaction uses up concentration, this time will change, okay? The amount of time it takes to do the reaction will change. It will get slower and slower and slower. All right, so your plot of 1 over a versus t, this will produce a straight line. You may have noticed that this looks like a y equals mx plus b again, and it is. So again, you can plot that. If 1 over a versus t gives you a straight line with a slope, that slope will equal k, and that will be a second order reaction. The equation shows how a depends on time, and this can be used to calculate a at any time of t, provided that we can get k and the initial concentration. So when a half-life of the second order reaction has elapsed, so again, t equals t1 half, which is where half of your concentration has disappeared, right? So by definition of half-life, it has to be where the concentration is half of your original. So if we substitute that in, we can then get it so we have each side being your initial concentration. So by definition, the half-life has to be this right here. Let's go ahead and clean that and solve that a bit so we can get it nice, clean, and easy to deal with. So when we go ahead and do a bit of solving, we see that we get this, which is 1 over the initial concentration equals K times the half-life. So when we solve for the half-life, that will give us the expression of our half-life for a second order reaction like we saw before. So again, this would be our half-life would equal 1 over K times the initial, or over the initial concentration. All right, so let's go ahead and determine some rate laws here. Butadiene reacts to form its dimer according to this equation right here. And so that's butadiene right there reacting to form the dimer. We have our concentrations right here. So this is our concentration. You'll notice it's disappearing over time. And this is our time right there. So first off, is the reaction a first order or second order? Okay, so one of the easiest ways to figure this out is, does it have a consistent half-life? So if we look at halves, this doesn't really have nice halves, does it? And so I would go ahead and do the math in this case, okay? It would be more difficult to try to do it graphically. It would be more difficult to try to do it off of a table like I was originally did in the first one. So first order or second order. So to decide whether rate law of reaction is first order or second order, we have to see, the easiest way, in my opinion, to see is to do it graphically. So we go ahead and plot the natural log versus time in a straight line. It's first order. If a plot of the 1 over the concentration versus time is a straight line, it is second order. So the data to do these plots would be this. That's the times versus 1 over. This is the time versus the natural log. That gives you these plots here. So we see the natural log versus time, which would be our first order, that is not a straight line. Our 1 over our concentration, that is a straight line. So that is a straight second order reaction. And that means this is would be your rate law. All right. Okay, I'm going to go ahead and solve this way. I'll come back then and explain how to deal with this without plotting, okay? All right, so our plot, we have our plot now, right? If you take that plot and you figure out the slope of that plot, you're going to have K then. So the slope will be equal to K. So we take the plot. The slope of the line can then be expressed as so, where the slope equals the change in y, which is that 1 over concentration. So all we have to do is take the difference between the two of these values over the difference in time, and that will give you your slope. So again, right here we have these values. This one right here is the values we're looking at. That's our second order. All we have to do is take the difference in these times and the difference in these concentrations right here. So this would be the difference here divided by the difference here, and that will give us this right here, which is our slope, or the same as K. That's K. So we use time 0 and times 6,200, let's say. We can find our rate constant from that reaction right there. So we take the 1 over concentration for time 0 for time 6,200. We put that over 6,200 minus 0, the times. We take those values, that's this right here, that's this, and we take that divided by that, and that gives us our K, rate constant. So the expression for the half-life of a second order reaction is So in this case, K equals that value we just figured out from part B. And the time zero concentration would be that first one on the table, the initial table, which was 0.01000 molarity, or our concentration at time zero. So we're going to then plug it in to our half-life expression, which is this right here based on our integrated rate law. By the way, if you look at the periodic table / equation table I give you guys, you will notice these things on there that you can actually just take and use off of there. So the initial concentration will be halved in 1,630 seconds if we plug these in. Again, this is K. That's the concentration of time zero. It's 1. We then solve, and we get that right there, which is this. Okay. No. I'm going to go ahead and look at the table here, and there's second order is never quite as easy as first and zero order. They're always a bit harder, okay? But there is a way you can do this, okay? So, if you remember your, where is it? There it is. Okay, so if you remember your half-lives, in the case of the first order half-life, it did not change. The half-life is always the same amount of time every time. So when we look at the halving concentrations, so we go from 1 to 0.5, 0.5 to 0.25, etc. It's always the same amount of time for a first order. If we then look at a second order reaction, this right here is going to, well, half-life is inversely related to the initial concentration, right? And so what does that mean? Well, that means if we look here, let's look at halving. So halving is somewhere in between here, right? So like 1,500 at least, right? So we look then and try to half it again. So half of this would be somewhere down here, right? And we see that this went from 1,500-ish to like a 3,000 seconds to half it, didn't it? That's a huge increase. That's because the concentration went down. The half-life is inversely related to your concentration. And so, when your concentration goes down, your half-life gets longer and longer and longer in a second order reaction. And so you can, by reading this table, determine whether it's first, second, or zero order. You will notice that there is only first, second, and zero order that you have to worry about for these reactions. Frankly speaking, there just hasn't really a need to determine or deal with third order. That doesn't happen. Nobody's ever experimentally proven that that's a thing. Tertiary order is an actual thing. And so we'll teach you information about it, but just know. Okay, so again, I know that this has to be a second order because the halving takes longer and longer and longer. By the way, if you're a little clever here and if you think ahead a bit, don't just wait for me to tell you everything, and try to use your critical thinking skills. If first order is the exact same amount of time every time it halves, and second order takes longer and longer each time it halves, then you could deduce that zero order probably does the opposite, doesn't it? That it takes less and less time, you might think. Okay? And we'll find out if that's true in just a little bit. I know, a cliffhanger. So you can see that you can actually skip a lot of work here, and which is actually kind of long and somewhat difficult work, if you just look at the equation and you understand the patterns. Okay? Again, work smarter, not harder. Okay, so the half-life for first versus second orders. So the half-life for the first order reaction, the half-life depends on K only. The second order reaction, the half-life depends on both K and the concentration at time 0. By the way, when you look at half-lives, one of the things you need to remember is when you're talking about Half-Life 1 versus Half-Life 2 versus Half-Life 3, the initial concentration is the previous half-life's concentration. Okay? So for example, if I'm looking at the next time it's going to half, the initial concentration was the previous half. Okay? So half-life for the first order reaction is a constant time. It's required to reduce the concentration of the reactant by half. Second order reaction, each successive half-life will double the preceding one. It will be twice as long as the previous one. So the rate law for a zero order reaction is going to be like so. So again, this is going to be rate equals K times the concentration to the 0th power. Now you can simplify this to being rate equals K. That's it. So if we integrate this, the integrated rate law for a zero order reaction is actually going to be the concentration equals negative K times T plus the initial concentration. You will notice that number one, this is a negative K because it's always going to be negative slope because your concentration always goes down with time for your reactant. The other part you will notice here is this literally is just exactly like setting your concentration versus time as a graph. So here we have our concentration versus time, and it's going to be a linear line for the zero order rate law, for the zero order reactions. And so our slope is just directly negative K, which is the rate constant. That's it. So the expression for a half-life of a zero order reaction, we can obtain that from our integrated rate law again. So again, remember, half-life means that the concentration at that time will be half of the initial concentration. And so we just substitute those in. So half your initial concentration equals negative K, the time of the half-life, so half-life, plus your initial concentration. Notice that that's actually fairly easy to simplify then. So again, we are going to subtract that over. We actually subtract each so we can get all positives. So right here we then have this, which again is this, subtract, subtract. And then we can rearrange it as half-life equals our initial concentration over 2K. Now, what does that mean? Well, that means that our half-life is proportional to our initial concentration. So as our initial concentration goes down, our half-life is going to, you guessed it, go down. Cool, huh? Our patterns hold. We can actually predict things. And so this is an example of a zero order reaction. Typically, zero order reactions are something that the rate limiting, what makes them take time, what is the holdup and how long this reaction is taking, is limited not by a reactant, but by a catalyst. Okay? And so right here we see the decomposition of nitrous oxide on a platinum surface. We can see here it doesn't matter how much of the reactant we have here. What's holding things up is how many of them can fit on the platinum. That's it. So what's really causing the rate of the reaction to be faster or slower is how much surface area you have here. More concentration is not going to make this faster. In fact, it may just bump things off here and make it even slower. So it's not going to help your reaction be faster. So consider your simple reaction, A going to products. You run this reaction, you wish to determine its order. What if you make a graph of reaction rate versus time? Could you use this to determine the order? So let's try sketching those three plots of rate versus time for the reaction. and see whether it's zero, first, or second order. Sketch those plots on the same graph, compare them, and try to defend your answer. And what you'll see is you kind of can, but you can definitely tell the zero order. That's not a problem at all. However, what you end up getting is when you get them, it would be much less reliable. It's much easier to get confused and messed up. Try it out and look at them, okay? This is really the critical thinking. These are meant for you to try to explore on your own. Now, the integrated rate laws for reactions with more than one reactant. So let's consider this following reaction here. This was that 3-reactant reaction we talked about before, right there. So our rate law was this. And so remember, this overall reaction was a 4th order reaction. Well, we didn't talk about a 4th order, did we? So let's assume the reaction occurs under the following conditions. So we have very little concentration of this. We have 1 molarity of this and 1 molarity of this at the beginning. So as the reaction proceeds, the BrO3- will decrease significantly. The Br- and H+ will almost stay the same. They'll decrease so little they'll have almost no meaning. So the rate law can be rewritten as so. And that's that throughout this reaction, your Br- and your H+ will essentially not be able to decrease because there's so little of this that when you subtract that number, you just round these right back up to 1. And so what we get is a pseudo first order reaction. And that's that the only reactant that's actually in small enough quantities for its change to matter is BrO3-. These Br- and H+, they're essentially constant. They don't change. And so they actually join the K to become K'. They actually get grouped up as constants. So their concentration changes don't really matter because the changes are so small as to be just rounded off or rounding errors. Now, the rate law would thus be pseudo first order, which would be this right here. Notice it looks like a first order rate law. We call this pseudo first order because we've set up our conditions to be like its first order. We can rearrange this right here to give us K on one side and K' on the other, like so. And so if you are trying to find the value of K from this, so you use this to solve, then you try to find the value of K, you can use it to find the value of K, like so. All right, so this right here is our summary table. This right here is what you should be comfortable with each of these relationships and understand, okay? All right, for which order reaction is the half-life of the reaction proportional to 1/K, where K is the rate constant? So if you remember all your integrated rate laws when we solved for the half-life, every single one of those had 1/K. That means that all of them, 0, first, and second order reactions, all of those, the half-life of the reaction is proportional to 1/K. For the first order reaction, the first half-life is 20 minutes. What is your second half-life? So for first order reactions, the half-life does not change. And so it has to be 20 minutes. So for a second order reaction, the first half-life is 20 minutes. What would be your second half-life? Well, it is going to be twice as long. And so that must then be 40 minutes. Okay. And for zero order reactions, the first half-life is 20 minutes. What would the second half-life be? Well, we've done the same. We've done twice as long, so it has to be half as long. And yes, zero order reactions are half as long. I find the easiest way to remember this is I find that most students find it the easiest to remember just to remember it in order. 0 first, second. And so 0 is half as long. Uh, First is same, and 1 is 1, right? So 1 is same. And then second order is twice as long. But honestly, if you look at the equations I provide on your periodic table sheet, then you will notice that you don't actually have to memorize any of it. You could derive everything I've just told you from those equations. However, no, you have to be really on your ball game to do it. Okay? So at a particular temperature, the half-life of zero-order reaction is 20 minutes. How long will it take for reaction concentration to be depleted by a factor of 8? All right, so what we're looking for, this is a zero-order reaction. So again, each time the half-life is going to change. Each time the half-life is going to become smaller and smaller, and this is going to halve more and more rapidly. And so depleted by a factor of 8. Well, that means that we have, well, how many halvings would it take to get to 8? So 2 would be your first halving, right? That'd be, you divide it by 2. So depleted by a factor of 2. Your second halving would be 2 times 2 for a depletion of 4. And your third halving then would be 4 times 2 for a depletion factor of 8. And so this is 3 halvings, isn't it? Okay, so our first halving in a zero-order reaction takes 20 minutes. Our second one would then take 10 more minutes, which would be 30 minutes. Our third one would then take half of that 10 minutes, which is 5 minutes. So we have 20 plus 10 plus 5, which would give you 35 minutes for 3 half-lives in a zero-order reaction. Reaction mechanisms. All right, so full disclosure, I am what's called an analytical chemist, and one of the things that just kills me about chemistry publications, especially organic chemistry publications, and I do teach organic chemistry as well sometimes, but well, I do it every year now, but is reaction mechanisms. They kill me. Most reaction mechanisms don't have any real effort to disprove them. They're terrible science. But understanding reaction mechanisms is very good for your understanding of how reactions can happen. Okay? And some reaction mechanisms are actually quite well documented, and a lot of work has been done to try to disprove them. They're actually very good, to be fair. So, the reaction between nitrogen dioxide and carbon monoxide is going to involve these following steps, and this will be what is known as a reaction mechanism. And most reactions will actually occur by a series of steps instead of all in one step. I mean, if you really thought about it before, every time we show you guys more than 2 things that have to come together, there's no way that 3, 4, even 5 things are all hitting each other at the same time to react, right? And so what always has to happen is you always have to do reactions in steps, okay? And these steps are your mechanisms. They're how the reaction occurs. And so this right here is an example of a reaction mechanism split into its steps. We have an NO2 reacting with another NO2. That gives you NO3 and NO. The NO3 from here is going to come down to this step. That NO3 reacts with carbon monoxide. That's going to give you NO2 and CO2. And so here we have a reaction mechanism. The overall reaction would be a summary of these reactions. You will notice that in reaction mechanisms, some reactions have a reactant, which will show up as a product down here. In a reaction mechanism, at least one of the products from the previous one will show up as a reactant below. And so NO3 shows up here. When we sum these reaction mechanisms together, we will eliminate anything that would be a spectator and be on both sides. Okay? So K1 and K2, these would be your reaction constants for these individual reactions. Those would help you determine rates. Now, in the reaction, NO3 shows up on both sides. It is what is known as an intermediate. Intermediate is a species that is formed and consumed during the reaction, but is neither a reactant nor a product. So it will not show up as an overall reactant or product. It is made and consumed during the reaction mechanism, during the reaction. Each of the reactions that we see in the total mechanism is called an elementary step. Typically, people just call them reaction steps or steps of the reaction, but the correct name is elementary step. That is proper. This is a reaction whose rate law can be written from its molecularity. And we need to define molecularity now. Molecularity, this is the number of species that must collide to produce the reaction presented by the elementary step. All right, so there are three different types of molecularity we need to understand. There's unimolecular, uni meaning one, so unimolecular means that only one molecule has to be there, doesn't have to collide with anything else, for the reaction to take place. Bimolecular is going to be the reaction that involves the collision of two species. So two molecules collide, this creates the reaction elementary step. That would be bimolecular. Termolecular is bullshit. I repeat, in case you were too shocked by me swearing. Termolecular is bullshit. There has never been a single confirmed case of a termolecular molecularity. However, I will teach you this so that you understand what the hell it is when somebody tries to pull the wool over your eyes and tell you bullshit. So termolecular, this is a reaction that involves the collision of three species. Now, to be fair, nobody has confirmed a termolecular reaction. Is it possible? Yes, you could have three things that all collide in the correct orientation at the correct time that then react. The likelihood of it actually happening is incredibly low. It would be incredibly slow, and it just is very, 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 very unlikely. But me saying that's impossible, it's not impossible, it's possible. I mean, it's just bullshit. It doesn't happen in reactions that anybody wants to wait around and see happen. Requirements of a reaction mechanism. The sum of the elementary steps must give the overall balanced equation for the reaction. If you take those elementary steps, you combine them all into a single reaction, has to give you the balanced equation for the reaction. The mechanisms must agree with the experimentally determined rate law. This is actually where the rate laws all come from, if you're curious. This is what is determining those. So yes, the rate law will reflect this mechanism. So here we see the various different elementary steps, their molecularity, and what a rate law for them would be. And so here we see a unimolecular. This is, of course, first order in this case, because you have A, that's all you need, you don't need anything else. Here we see an example of a bimolecular reaction, or elementary step. In this case, A has to run into A, they collide, they react. This gives us a second order reaction. Right here we see another bimolecular, in this case A collides with B. And their collision is a reaction, in which case it is a second overall with first order to A, first order to B, with respect to B. Here we see an example of a termolecular reaction, what that would be, and this is A colliding with A, at the same time it collides with B. They all have to collide together at the exact same moment so that they react and form this. Let's see, our products. Again, this would be another termolecular. There's three different ones. That's all that is. So the balanced equation for the reaction of gaseous nitrogen dioxide and fluorine would be so. So right here we see this reaction. It produces this product right here. So if we determine the experimental rate law, that would be the rate equals K, the rate constant, times this concentration right here, times the concentration of fluorine. Notice again, these coefficients have nothing to do with the orders. Please do not get that confused. So these orders are first order with respect to this, first order with respect to this. So let's try suggesting a mechanism for this reaction. So this is our suggested mechanism right now. We have NO2 runs into F2. These react to form NO2F plus F. We say this is a slow step, meaning it takes a lot of time for this to go through. Now, this F right here is going to run in with another NO2. This right here is going to give us another NO2F. And so if we sum these together, the F's are intermediates. Those will cancel. These NO2, that would give you two NO2s, right? This would give you one F2 on the reactant side. And this would give you two NO2Fs on the product side. Does that match our overall reaction? Yes, it does. Okay, so that part's good so far. All right, the next thing we have to figure out is our slow step matching with our rate law? Now, why do I only look at my slow step? Well, let's think about this real quick. Okay, so let's say I'm commuting. I know that a lot of us aren't really being able to get out a lot, but let's say that I'm commuting to work or to school. And so my drive is an hour long. Now, it takes me 1 minute to walk out to my car and get in my car. What part of that am I most interested in when I'm talking about how long it takes me to get to school? Do I talk about the 1 minute time it takes me to get in my car and go, man, if I could cut down that 1 minute time, I'd really get to my school fast? Or do I talk about the 1 hour commute drive that it takes to get to school? If I could take this shortcut right here, cut off 30 minutes, man, I'd get to my school really fast. Well, of course, I talk about the slow step, right? The slow part. That's the one that matters. That determines how fast I get to my school. That 1 minute walking out to my car doesn't determine anything. It's so fast compared to the 1 hour that it just doesn't even matter. And so, whenever I do a reaction mechanism, the slowest step is always the one that determines how fast or the rate of the reaction. The fast steps don't matter. They're fast, they're going to happen so fast they won't be meaningful. They won't affect your rate. So right now we see that if we look at this, we would see that we expect NO2 colliding with F2, so an order 1 and an order 1 for a second order total, to be our rate determining step. The step that would determine this rate law right here. And so we see that we have an NO2 first order, F2 first order. That actually makes sense, doesn't it? Because look at that. That is telling us that NO2 has collided with F2 for this reaction to go forward, which is your slow step. Okay, very good. And this right here shows you the work for these. I like doing them without the work sometimes because frankly I feel like you guys look at the work and don't listen or try to understand. You don't work it out in your own heads. You just look at it and go, I can do that. And then when you try to do it, you can't. Okay, so we see this right here is taking these reaction steps. We sum them up. We cancel those F's. And we get our overall reaction. Excellent. And so we do the second step. Yes, that makes sense. The second step is also okay. So we have failed to disprove this mechanism. So currently this mechanism is acceptable as we have we have satisfied our requirements. All right, so this is the collision model next. the molecules must collide to react. So only a small fraction of collisions will actually produce a reaction. What this does is it postulates that the energy comes from kinetic energy possessed by reacting molecules before collision. So collision kinetic energy furnishes the potential energy needed to enable the reactants to rearrange to form products. Another way of thinking about this is if molecules are bouncing around really, really fast, then when they collide, they're going to have more energy to cause them to get closer and bond or do a reaction, right? Or break something apart. The other part of this is the more they bounce around, the faster they're bouncing around, the more they're going to bounce around and manage to hit the correct angle to collide where the oxygen is close enough to the whatever to react with it, right? So part of what you need to understand for the collision model are several key concepts that are going to be important from here on, okay? So activation energy is one of these concepts that really just is important as a scientist, period. Anybody that requires science to do their job needs to understand activation energy to some degree. So activation energy, this is the energy that must be overcome to produce a chemical reaction. The rate of the reaction will depend on the size of the activation energy. If you have a high activation energy, the reaction will be slow. If you have a low activation energy, the reaction will be fast. Okay, the way I always like to talk about this is think of activation energy in two sort of concepts. So first we have the concept of walking to a destination. And so in between us and our destination, there's a tiny little rise in the road and we just step over it. Okay, no problem. We get there quick, right? That was not a problem, doesn't cause us any issues. So that's a small activation energy and it makes the reaction fast, or us walking there fast. What happens if we put Mount Everest in between us and our destination? That's going to take some time, isn't it? And so Mount Everest will take us a very considerable amount of time to scale. Could be weeks, could be months, could be never. I'd probably, never get over it. So that is going to be a large activation energy, greatly increases the amount of time it takes us to do our reaction or reach the destination, right? Now, let's think of it like this as well. Now, we know that gasoline burns and it does so spontaneously. Once gasoline's lit up, it's hard to get it to extinguish, isn't it? It'll just keep burning. So why does your car not explode right now? You have gasoline in there. It's spontaneous. And once it goes up, it'll just keep going, right? It'll just burn your car. Why is it not burning right now? Well, the reason for that is you have not reached activation energy. So right now, your activation energy is too high for the ambient temperatures to overcome. If you were to put a match in there, a spark, that would overcome the activation energy and cause your reaction to proceed forward. And then, of course, it is a self-fulfilling process, right? The energy given off by burning then overcomes the activation energy for other molecules in the reaction. So there you go. Activated complex. Another way of saying activated complex is transition state. This is actually going to be the more common way of saying this, actually. So the arrangement of atoms found at the top of a potential energy barrier. So activated complexes or transition states, these are going to be the arrangement of your atoms that you find when you're at the top or your activation energy barriers. Okay, and I'll show you a barrier right here. So right here, this is a energy diagram right here. So here we have the energy. Here we have a reaction, progress of a reaction. So this right here is going to be your reactants. They're on the left side because reactants are always on the left side. There you go. So you have your reactants. What you're going to do is to overcome your activation energy, you have to put energy into your reactants. This would be like heating them up or introducing a spark, right? Or just being high enough temperature for this reaction to occur. To overcome the activation energy, what you're really doing is you're forcing two of these BRNOs into a state that they don't really want to be in because they will repel each other due to how close they are. Their electron fields, those electron wavelength fields that we talked about before, remember we talked about the electron clouds. Those are negatively charged, right? So when we push these two BRs next to each other, we're causing these negatively charged electron clouds to repel each other. And so yes, that takes energy to overcome that. And that's your transition state right here. Now, once you've overcome that energy, it can then go downhill because the reaction takes place. You make Br2, which is the Br2 right here. You break this, and you have two NOs. Now, that will give you back energy. In this case, this is actually an exothermic or an exergonic reaction. In this case, we don't know if that's delta H or not, but delta E means exergonic. That means that this is actually releasing energy because it goes further down in the products than the reactants were. See how the products are lower than reactants? That's giving off energy. If this was above, that would be sucking up energy. Okay, and so now you've learned how to determine this is reactants, that's products, that right there on the top is the transition state, and the difference between reactants and the transition state in energy, that is the activation energy. Right here, this is a graphical representation of those formulas. See, those are the BRs right here. To have the reaction take place, these have to collide and merge together close enough to bond. That's going to, of course, suck up a lot of energy to do. And this is then going to release energy when they break these single bonds here and finish forming this bond here. All right, so the collision model. Only collisions with energy greater than the activation energy are able to get over the barrier. So right here what we see is they're at a temperature. Only a certain amount of the molecules will have enough energy that if they collide, that will overcome the activation energy barrier. The rest of them are a bit like bumper cars. They bump, then they repel each other, nothing happens. So think of it a bit, the best analogy I can give you here is like car accidents. So you may have seen, especially if you go to Europe, especially Southern Europe, people bumping each other's bumpers, and they do it at a fairly low speed, and so it doesn't really cause any major damage. And that's fine, right? And so, not great. Americans will get really uppity about it and be very angry about it, but for the most part, most of the world, people don't care. And they just, little bump, oh well. However, if you did that same sort of collision and you're on the highway because you have a lot more kinetic energy, it's going to cause parts of the car to go flying off, right? And possibly kill the people involved. And so that would be the difference between a low energy, low temperature, right here, the blue one, where we have very few of the molecules going fast enough to react, versus a higher temperature, which has more kinetic energy, which more of the molecules will then have enough energy that once they collide, they will react. Again, what you're doing is these molecules here above this E of A have enough energy to overcome the barrier that is the transition state or activation energy to proceed through to the reaction. Now, you will notice that if you look at these temperatures, the higher the temperature, then the larger the number of molecules that will overcome this activation energy. This is an exponential increase. So, this increases exponentially. This is why, for example, if you try to bake something or cook something, if you bake it at 350 degrees Fahrenheit, it bakes it may take an hour to bake, right? If you bake it at 400 degrees Fahrenheit, it'll take about 30 minutes maybe, or closer probably to 20 minutes to bake. It's an exponential increase, it's not linear, okay? So, right here we see this represented using formula. So this is the mathematical representation of it. So the number of collisions with the activation energy equals your total number of collisions times E to the power of the negative activation energy divided by R, the gas law constant, times T in Kelvin, temperature in Kelvin. Now, this term right here that we saw up here, this E to the negative EA over RT, again, these are all in the power of this. This is called the fraction of collisions with the energy of EA or greater at that temperature of T. That's what that represents. Okay, so by the way, this formula right here, this is more useful than just this collision model, okay? This actually helps you determine pretty much any energy states that depend on temperature. They will have this same sort of form with very, very minor changes to this. So this is actually a very incredibly useful formula. If you go into graduate work in biochemistry or chemistry in general, remember this place. You will have to find this at some point. All right. I speak from experience because I did not remember and I had to spend like an hour looking for it. Damn. All right, so this is the orientation, how that matters. So right here we see the BRs oriented next to each other. So when they collide, they can merge and form BR2. Here we see another example of BRs. When they collide, they'll merge and form BR2. Here, that's impossible. When these collide, the O's are the ones that are colliding. And so the BRs will not be able to merge and make BR2, will they? And so this collision can never result in a reaction. And so that's what the importance of how they collide is. The collisions must involve enough energy to produce the reaction. Collision energy must equal or exceed the activation energy. Relative orientation of the reactants must allow formation of any new bonds necessary to produce products. If you collide with the opposite side of the molecule, you're never going to bond. Okay? These are the requirements for reactions and this reaction collision mechanism or model to produce a reaction. So this right here, let's take those requirements, and then we can go ahead and make a constant, a rate constant based on those. So this right here is our rate constant. Same rate constant we saw all those times before. That's that same K. This will equal the collision frequency, which is Z. P will be a steric factor. It'll always be less than 1. So this reflects the fraction of collisions with effective orientations to them. So this tells you how often they'll collide. This one tells you how likely those collisions are to be meaningful, to be effective in bonding, or to be effective in reacting. This right here is the temperature component and the activation energy component. So this is the fraction of collisions that will have sufficient energy to produce a reaction. So, for example, again, if you collide 1,000,000 times, but every time you collide you're only going a mile per hour, you're never going to cause that bumper to come off, right? Or you're never going to really hurt yourself if you just tap the table, even if you do it 1,000,000 times. But if you do it really, really hard, that's where you can get a reaction, like hurting yourself. So, this right here is showing you
how hard you're tapping, how hard you're colliding, right? This is showing you how often you're colliding, and this one's showing you the orientation you're colliding. So again, that would be like if you collide with the very, very edge of the table, you'd be more likely to hurt yourself or get a reaction, right? Okay, so this is actually the Arrhenius equation, and this is the important part that you're going to, if you go into chemistry, any sort of research in chemistry, this equation will show up all over the place, because this determines how many molecules are emitting light, determines how many molecules are doing a tremendous number of things, okay? In a tremendous number of different states. It's not actually just for reactions. It's for any energy states. So the Arrhenius equation, this is K equals, this is the Arrhenius frequency factor right here, times this E to the power of negative activation energy divided by RT. Remember, these are both in the denominator. Okay, you can actually solve this to get another form of it. So if you take the natural log of both sides, you'll get this right here. And that gets rid of that E right there. Now, that will give you this. You will notice, if you look very closely and blur your eyes a bit, that this will give you a linear equation, which is natural log of K, that's your Y, equals, right there's your slope, right there's your X, and right there is your y-intercept. All right, and there we go. If we plot that, we can get a slope. So we can then solve for the activation energy graphically by just getting, actually we can solve for activation energy and the Arrhenius frequency, the Arrhenius factor, just by collecting K's and 1 over T's. So taking the rates that reactions run versus their times. And then plot them, and you'll get these slopes. All right, so let's think critically a little bit. There are many conditions that need to be met to result in a chemical reaction between molecules. If all collisions between molecules resulted in a chemical reaction, how would life be different? So the best way I can describe this is reactions would just be vastly more common. And so you put gasoline in your car and you rub your car the wrong way, boom, there goes your car, it blew up. Reactions would be vastly more common. They would require, if all collisions resulted between molecules, resulted in chemical reaction, right now you couldn't live because the oxygen would be oxidizing you, right? It would be chaos. So the rate determining step of a multi-step reaction can be described as the slowest, fastest, first step, last step. Well, it is the slowest step, right? Slowest is always what determines how fast something is happening. It's the rate determining step. So here's an interactive example. We're going to determine an activation energy. The following reaction was studied at several temperatures. And so this is a reaction right here. 2N2O5. You got it. You can look at it. I'm sure you can read that. If you can't read that, please send me an email so I can send you back to chapter 1 and help you out, because that will be detrimental. So values of K were obtained. So here we see values of K, and here we see temperatures. Let's calculate the value of E sub A, or activation energy, for this reaction. And so you can calculate the values of natural log K and 1 over T. You could then construct a plot like so. And so right here we have 1 over T and the natural log of K. Notice that these values right here are in Kelvin, so you always have to convert to Kelvin first. All right, so we plotted this. We then take the slope, and the slope gives us a 1.2 times 10 to the 4th K.
And so we have our slope based on our plot. And that means that we can determine the activation energy by just multiplying this slope by r and getting rid of the negative sign. And so we do that work. We take our value, r, multiply it by the slope here, and multiply a negative sign so that we can get rid of the negative. And that gives us our activation energy, which is 10 to the 5th joules per mole. And there we go. So at temperature 1 were our rates. This is another method we could do this. Honestly speaking, most of you are probably going to struggle with graphing. I usually find that takes longer and requires more work, ultimately. So I would actually overall recommend this alternative method here. So if we take temperature 1, where the rate constant is K1, we can go ahead and then set a second state, which would be temperature 2. And so this would be our second state, temperature 2, rate constant 2, which matches up to that. We can then take one and divide it by the other. So we subtract the first equation from the second equation. I'm sorry, subtract. I get a little off kilter when I sit here lecturing to these computer screens. They don't provide me very good response. All right. So we subtract our second state by our first state. So literally we take this minus this, this minus this, this minus this. And that's what you're seeing right here. And so this minus this gives us this, which is natural log of this one divided by this one. And that's what subtracting natural logs do. By the way, if you had a plus here, it would be K2 times K1. Anyways, this one then is going to be these two terms added together. So you see that's negative here. This negative turns this positive, which is this. These will cancel because you have plus natural log of A minus natural log of A. That will give you 0, which don't have to write. All right, so the next thing we're going to do is we have this term over here. This right here, we can go ahead and remove the t's from here and get the e's of a's that we cannot solve. So they are all in one term. And so we go ahead and remove from each of these an E of A, activation energy, divided by R. That leaves us 1 over T1, which is the positive one, that's why it's first here, minus 1 over T2, right here. And we go ahead and put parentheses around those. Now we can just substitute our values from the table in. And so we substitute our values of the table in, we solve, we notice that we'll get the slope again equals E of A over R, same as we had before. So we'll end up with the same value right here. Okay? And that's it. There you go. You just solve and it's done. Don't forget to do these in parts. When you have equations that are fairly complex like this, I highly recommend you not try to enter them all as one piece in your calculator. Take a piece of scrap paper and just solve this part first, this part, and then do these processes. Natural log of this, and then take this and divide it over. Just do it in pieces, okay? If you try to do it all as one, I usually find that that's about a third of student mistakes where they screw up and get the wrong answer in problems. Is they think they know how to use their calculator and they're either too tired or they don't actually know how to use it. Okay. Critical thinking. Most modern refrigerators have an internal temperature of 45 degrees Fahrenheit. By the way, if you think I'm a little sarcastic and a little tired, I'm honestly not like that normally. It's just lecturing my computer kind of brings the worst out in me. I'm sorry if you get that from me. It's exasperating, and I have to over-explain myself. Most of the time, you guys are much better than what I think is necessary.
And so most of the time you guys pick up much faster than what I'm doing here. What if refrigerators were set at 55 degrees Fahrenheit in the factory? How would this affect our lives? So instead of 45 degrees Fahrenheit, we have it set to 55 degrees Fahrenheit. Well, I told you that temperature is an exponential increase in reactions, right? Well, wait a second. Are reactions something that are only inorganic and not to do with biological organisms? No. Reactions are what all life depends on. They're how fast we can grow. They're how fast we can metabolize. They're how much energy we have to do things. So when you see food rotting, it's because of the temperature. The lower the temperature something has, the slower it's going to take for that food to rot. The higher the temperature, the faster it can rot. And that's why typically if you look in your freezer, yes, things get freezer burnt, which is actually ice crystals bursting the structure, but they do not typically rot in the freezer. And that's because it's so low temperature, it takes a very long time for bacteria to grow in a freezer. Whereas in a fridge, you can see a little bit of rotting, but a lot slower than you would see on your kitchen counter, right? And so, this 10-degree difference, this is probably a 10 degrees Celsius difference would typically be about doubling in speed of a reaction. A 10-degree Fahrenheit would be a bit less than doubling, okay? It would be somewhere more towards like half of that. So it would be like a 50% increase in how fast these things would rot. So it would be a considerable increase, but it wouldn't be doubling or anything. It would just be like things would rot in a day or two instead of taking a week. Okay, so let's consider the following potential energy diagram, which is right here. Which letter shows the activation energy of the uncatalyzed reaction? Now, I did not mention this before. Catalysts act on the activation energy. So what a catalyst does is a catalyst, which an enzyme is a biological catalyst for all of you biology majors. What a catalyst does is it is going to lower the activation energy. So it will then lower that activation energy. That is going to increase the speed that the reaction can go in both directions. Okay? And so, yes, a catalyst does actually increase the speed that the reaction goes both in the forward and the reverse directions. A catalyst does not affect whether a reaction will go forward or reverse. It just makes everything faster. Okay? And yes, that is an enzyme as well. Enzymes are just biological catalysts. That's what they are. So, which letter shows the activation energy of the uncatalyzed reactions? Now, I get so many people that will give me C. But that has nothing to do with this reaction, does it? See, this is going down to some imaginary zero energy point, which frankly has nothing to do with real molecules, okay? There has never been any molecule we have ever been able to view or see that was zero energy. So this is just a total, there is a zero energy that we've set. We don't even know if it's zero energy. There's nothing we can know about this point. That will be a major, major breakthrough. I have a funny feeling there's actually energy below the zero we've set. But anyways, that's a spectroscopist for you. Because as far as we can tell, things keep rotating at supposedly zero energy. Anyways, that's besides the point. That's a much more advanced chemistry topic. If you ever want to talk about it, you can, email me or something. Okay, so it has to be A, doesn't it? Right here, this would be what we have to overcome, the transition state. We have to overcome activation energy. So the difference between our reactants and that transition state will be the activation energy. There you go. Now, which letter shows the change in energy for the overall reaction? So going from reactants to products, what would be that change in energy? Well, that's obviously D right here, right? That would be the energy difference between the reactants and our products. All right. One of the things I would like to go ahead and mention at this point, we'll go in more detail, but you won't really get it until organic and biochemistry if you go on to that, is that how most catalysts and enzymes actually work is rather than just straight out lowering this activation energy, they actually change the transition state. So what it usually does is it breaks up the transition state. So instead of having one big bump here, that top is a very, very high energy transition state, it would have multiple smaller transition states, that their overall energy is lower. And so that actually would be how most catalysts and enzymes work. Most enzymes work by binding the reactants first, then it lowers the amount of energy for them to collide in the correct orientation, then it releases them. That's how most enzymes work, if you're curious. So here's another interactive example of a course for determining the activation energy again. We have this reaction again. Right here is the reaction. At 550 degrees Celsius, the rate constant for this reaction is 1.1 liter mole second. At 625 degrees Celsius, the rate constant is 6.4. And so we can see it goes up a lot. Use these values, calculate E of A for this reaction. So again, this is a tabulated form of this. What we've done here is we've gone ahead and converted these to Kelvin since we're going to need them in Kelvin. So again, this is state 1 here. This is state 2. So we're going to go ahead and plug these into our calculation, which again was that natural log of our K values here, state 2 versus 1, equals the activation energy divided by the R, which is again our gas law constant, times 1 over T2 minus 1 over T1. And so we plug those into that previous equation we hadn't used before, and we go ahead and do the math. Don't forget to do it in steps. It's the easiest way to do it. And then that's going to equal this value right here, which is our activation energy. And there we go. That's it. Okay, this is a theoretical example of a catalyst. It's a nice way to look at in your mind, but honestly, it typically this is not what most potential energy diagrams will look like when there are catalysts involved. It's usually broken up into pieces, if you're curious. So again, this is what a catalyst will do. A catalyst is, by definition, a substance that speeds up a reaction without being consumed itself. That's very important that you realize that it does not consume itself. So if it cannot be a reactant, it cannot be a product. It cannot be something that will be consumed. If it is used in the reaction, it has to be regenerated at the end of the reaction. It cannot be consumed by the reaction. And so here we see the on-catalyzed pathway. And we see that it has a higher activation energy. So what a catalyst does is it lowers the activation energy. What this does is it makes more of these collisions, if you will, productive. And thus it will make the reaction faster by lowering the activation energy. You will note that the reaction, if there's a reaction going from products to reactants, the reverse reaction, would also be sped up by this same thing. It would lower this activation energy going backwards as well. So right here we see this in terms of the energy and heat. So here we see an on-catalyzed reaction. Only a relatively small number of these collisions would have enough energy to overcome the activation energy. Here we see that due to the catalyst, a much larger segment of these collisions would be effective, would cause the reaction to go forward. So let's talk about heterogeneous versus homogeneous, the different types of catalysts.
So a heterogeneous catalyst, this is mostly going to involve gaseous reactants being absorbed on the surface of a solid catalyst. That's the most common you'll find, especially in industry. Overall, though, heterogeneous, hetero meaning different, right? And so the catalyst will be a different phase than the reactants. Okay? You cannot mix the reactants and catalysts. There you go. That's what a heterogeneous catalyst is. The big thing that we have to be concerned about when we talk about heterogeneous catalysts is, especially for the gas phase reactants reacting using a solid catalyst, is adsorption. Notice the D part of that, adsorption. This is getting a collection of one substance on the surface of another substance. This is actually when you see water sticking to the surface of a glass or a can, that would be adsorption. Or, for example, gaseous molecules sticking to the surface of a solid catalyst. That would be adsorption. Right here we see an example of adsorption. This is the hydrogenation of ethylene. Excuse me, I need more water. All right, and so what's happening here? Hydrogen reacts with ethylene, and excuse me, it does so by first absorbing onto this catalyst surface, which is your heterogeneous catalyst, of course. And then these hydrogen molecules will then separate on this surface. They'll be stabilized on this surface. They'll skitter along it. When they collide into the ethylene at the appropriate angles, that will cause a reaction. And that gives you this product right here, which is ethane. And then the next part is the ethane will have to be released from the catalyst, thus forming the gaseous ethane, and which you can then use in your grill or whatever. So, the oxidation of gaseous sulfur dioxide to gaseous sulfur trioxide. So dust particles and water droplets will catalyze the reaction between SO2 and O2 in your air. I really should do these reverse order. Okay, so acid rain. This is acid rain. And what it is dust particle and water droplets in the air. They will absorb SO2 particles and O2 particles. The SO2 typically given off by improperly functioning coal plants. The majority of the SO2 in the atmosphere right now is being given off by China and Russia, though China has been getting much better in the last 5 years or so. But they are still the majority of the SO2 in the atmosphere. Ironically, that was actually holding back global warming, but it was causing sulfur acid rain and acidification of the ocean and all sorts of other negative connotations. So, when these react in the air, they react on dust particles and water droplet surfaces. The negative aspects of them, of course, is that toxic air pollutants are formed. The gaseous sulfur trioxide is toxic. It can further react to form acid rain. If you look at any old stone buildings, especially limestone buildings, you will see they're rounded and many of the details have been destroyed by acid rain. The positive aspects of this can be used in the manufacture of sulfuric acid. Sulfuric acid is one of the industrial components we need to make many of the products around you. It actually is very useful. It's actually a catalyst in hundreds of reactions, so it's very useful. Utilized in the catalytic converters in automobile exhaust systems, which ironically actually help to convert NOx and prevent the pollutants that are most common in the United States. So right here, this is actually the catalytic converter from your car, motorcycle, whatever. What you do is in your engine, because of the high heats, you can have unburned hydrocarbons, which are little fragments of HC,
which we're not showing you how large these are. This is carbon monoxide, and this is what's called NOx, NOx. It stands for NO1, NO2. And these are the components that make up photochemical smog, if you're curious. That's the smog you'd see in places like New York and mostly LA. LA has probably the worst problem with smog, not necessarily due to them, due to their environment that the smog is released in, causing smog to be much more prevalent. Anyways, a catalytic converter that's properly functioning will convert these into CO2 and H2O. Now, let me point out, many people, due to the debate on global warming, have a misconception that CO2 is this incredibly toxic, terrible substance. It is the substance you breathe out. If you don't know this already, in the second semester of chemistry, which is a little bit concerning, all CO2 is the same. CO2 you breathe out, CO2 that comes out of your car, CO2 is CO2, okay? Carbon dioxide is carbon dioxide, no matter the source, it is carbon dioxide. They do the same things, they have the same chemical, physical properties, they are carbon dioxide, okay? Doesn't matter whether it comes out of you, a plant, your car, anything. Cow, doesn't matter. So, these components right here are actually toxic, okay? Carbon monoxide is why you've probably heard of people committing suicide by leaving their car running in their garage. Ironically, a new car with a properly functioning catalytic converter, you could sit in your garage for 12, 24 hours and it would not affect you, because the catalytic converter actually converts so much carbon monoxide away from being carbon monoxide and CO2 that you just can't suffocate yourself to death. So that suicide method only works with shitty cars. But, and that happens a lot nowadays, actually. It's kind of a silver lining, I guess, if you will, in an otherwise very dark topic, is that many people that have financial problems are concerned and want to kill themselves because they're going from very high financial to a very low financial then. And so typically they have very nice cars and they try to kill themselves with those nice cars, and it does not work. And so their family or anybody finds them, and a lot of times they get help that they need. So that is a silver lining, if you will. Catalytic converters save lives. The improperly catalytic converter will of course let these through. That's how that works. Anyways, it also converts the hydrocarbon, which is the black soot you see coming out of some of the cars. That is an improperly working catalytic converter. Anyways, so homogeneous catalyst. This exists in the same phase as your reacting molecules. So if your reacting molecules are liquids, this will be a liquid. If they're solutions, this will be a solution with them, etc. So consider the catalytic behavior of nitrogen oxide towards ozone. Here we see nitrogen and oxygen, and they react together to make nitrogen oxide. So NO catalyzes ozone production in our troposphere. Troposphere is where we live, by the way. In the lower atmosphere, the NO is produced in high temperature combustion processes in the presence of nitrogen. This is actually where the NO in car engines come from, because 71% of the atmosphere that we're burning in our car is nitrogen. Normally those don't react, but if it's high enough temperature, they will react with the oxygen, which is what we're using to burn the fuel. And this creates NO, nitrogen oxide. So significant amounts of this nitrogen oxide escape into the atmosphere from these reactions. Interestingly enough, 90% of this nitrogen oxide that's being released due to cars is actually due to less than 5% of the vehicles on the road, which are the vehicles that do not have functioning catalytic converters. So an interesting little piece of information there. Most of it is properly converted using catalytic converters, and it doesn't cause any problems. So NO2
So NO can react then with oxygen in the atmosphere to form NO2. NO2 absorbs light and decomposes as follows here. So if you have released NO2 in the atmosphere, when it's a sunny day, it'll absorb light, it breaks down to NO and what's called free radical oxygen. This free radical oxygen can combine with O2 in the atmosphere to form ozone. Ozone is a powerful oxidizing agent. This can react with other air pollutants to form many different toxic substances, and ozone is actually toxic in and of itself. Ozone is, if you're interested, what you smell after a lightning storm. It's that sort of stinging sense in your nose. Anyways, this, by the way, is why the smog is much more visible and prevalent when you are in some place like Florida or California, is because they have a lot more sunlight, and so this reaction right here happens a lot more often. Places like New York have less sunlight, and so this reaction doesn't happen as often. That's the real difference, actually. Not that California doesn't have another problem, which is they're more spaced out, thus they have a lot more cars being driven around. But anyways, it's the sunlight is the real key factor there. So if we summarize these reactions, what we can get from them is that 3/2 O2 will give you 1 ozone. All right, so in the upper atmosphere, the presence of nitric oxide will actually lead to the depletion of ozone. This really isn't as much of an issue. This is sort of a beside the point thing. There's not a huge amount of nitrogen oxide being released in the upper atmosphere. That's not a massive concern that people are really just bugging out about. But anyways, yes, it can really deplete ozone in the upper atmosphere, and this is such a. Anyways, this is an example of a reaction that's interesting. And yes, if you release nitrogen oxide into the ozone layer, it would deplete ozone. However, we can see here that also can create ozone anywhere there's less ozone than the ozone layer, which would build up in the ozone layer or on ground level. So it's kind of a funny thing that your book does. But anyways, ozone, if you're curious and you don't know what ozone is, it's the ozone layer is what helps to absorb ultraviolet radiation from the sun. Ultraviolet radiation being one of the leading causes of things like skin cancer. And there are actually versions of ultraviolet radiation that are high energy. Waves of ultraviolet radiation, those are actually lethal on exposure for less than 10 minutes. So they actually could kill all life on the planet. But they don't, because there's an ozone layer. Freons. Now, freons was an example that you may not know this, but back in the before the 1970s, humanity actually was on the verge of destroying all life on the planet. I am not talking about global warming. Oh my goodness, the water's going to increase by 20 feet. No. Global warming will not come anywhere near destroying all life on the planet. It won't even come near killing all humans on the planet, okay? Global warming will cause a huge amount of property damage, many deaths, if something isn't done about it. It will cause the climate to change and how we have to live on this planet to change, yes. But it is not an extinction level event, all life's gone. Freons were an extinction level event that all life on the surface of the planet and about 10 meters or so down into the water, gone. Dead, no more, it's over. And what this was is it's a group of stable, non-corrosive compounds. So that sounds very nice, right? They're stable, they're non-corrosive. So the original testing with freons in lab conditions went, hey, these things have no effect on anything. They're wonderful. No pollute that we don't even have to worry about them. They won't cause any damage at all. However, the problem is that when freons get to the upper atmosphere above the ozone layer, they start interacting with high energy UV radiation. And unfortunately, that energy is actually great enough to overcome their activation energy, and it does this reaction right here, which causes a release of free radical chlorine. And so this freons, which were formerly used as refrigerants, they were used as repellents in aerosol cans, um, they actually started causing ozone layer depletion. And if we had broken down and destroyed the ozone layer completely, and we passed what's called the Montreal Accords, is what started this road to recovery, which we have essentially recovered at this moment. Our ozone layer is essentially recovered as of right now. It's supposed to be completely 100% recovered, no difference from before, uh, in the next like 2 to 5 years, I think, if I remember correctly. But freons, by the way, if you're curious, yes, I'm a PhD in chemistry and geosciences. I also do, environmental chemistry if you're curious. That's why I have so much about this. Anyways, so freons, the main one that gets talked about the most is Freon 12, which is this one right here. However, freons were just compounds that were similar to this. They could have more chlorines or fluorines depending. This migrates in the upper atmosphere. When it decomposes in the presence of high energy light, like the upper energy of UV radiation, it releases the free radical chlorines. These free radical chlorines are actually a catalyst, and so this free radical chlorine catalyst helps to decompose ozone. Now, in the ozone layer, that's a big problem. Ozone is supposed to be used to absorb UV radiation. If you destroy and use up all your ozone in these reactions that are catalyzed, notice catalyzed means that it's not used up, that you have chlorine still there, it does not get used up. It just uses up your ozone and makes O2 out of it. Then they can no longer block the UV radiation, which is harmful to living organisms, especially the high energy UV radiation that we're talking about here. And so that high energy UV radiation, it will destroy all plants, animals. Human will die from high energy UV radiation, usually on the order of about 10 to 20 minutes. You can sterilize hospital equipment with this. Bacteria will die from high energy UV radiation. You can sterilize water from it. Many water purification plants use high energy UV radiation. This was banned, freons were banned by international agreement due to their environmental concerns. It is the only environmental pact that was truly successful. And if you ever take some environmental chemistry or look this up, it's actually very fascinating because it's one of the few times that people pulled their heads out of their butts and went ahead and came up with a solution for the corporations to use, and then came up with steps, an action plan that goes, okay, you're using freons right now. We replace them with this, which is less harmful. Then we replace them with this after we research and develop and start making it cheap to make. And then problem solved. After 30 years, bam, everybody agreed onto it. And they even gave the technology to nations that were developing so that they didn't have to make freons and use them. So it was a very successful environmental legislation worldwide, which honestly, there just has never been anything quite like that since. The current plans for global warming are comparatively ridiculous. They're essentially saying, you're causing global warming. Stop. That's the current planning. And some of them go a little bit better than that. You're causing global warming. Fines. Stop. None of them come up with a real action plan for the last 30 years of how to actually successfully replace our dependence on fossil fuels. Which you could have actually done with nuclear if you're curious, but we can get into that when we go into nuclear and everything else. Anyways, we're finally getting to the point now, after 40 years of effort, where something's actually successfully happening. But, oh, good God. Anyways, substitute compounds are now being used that can completely replace freons and do not cause this breakdown of ozone when they reach the upper atmosphere. An interesting side note is freons actually did cause global warming as well, if you're ever curious. But in comparison to all life wiped out on the planet, global warming was less of a concern. Consider the following potential energy diagram. Which letter shows the activation energy of the catalyzed reaction? So that obviously has to be E right here, right? This is the catalyst, is reducing the activation energy. And so the inactivation energy after catalyst is this right here. Okay, folks, you take care. Sorry that you had to go through a number of different side notes. Hopefully they were interesting and help you learn the material. Otherwise, sorry. You take care. Have a great night.